So, in this lecture we are going to look at optical lithography, in particular contact and proximity printing process. So, in the last lecture we saw in detail about resist processing and what are all the applications of resist, but in this lecture we are going to look at what is the imaging technique one can use in order to transfer the image onto the photoresist. In particular, we are going to look at contact and proximity printing. So, this is something that we already saw earlier. We have three type of optical lithography system: contact litho, proximity litho, and projection lithography. So, in this particular lecture we are going to look at contact litho and proximity lithography. If you look at the system itself, it's very similar, almost same. In fact, we are going to use the same system to do both these type of printing. So, there is a light source, and then there is a illuminating optics. So, this illuminating optics is trying to profile the beam, and then it is going to uniformly expose the mask that we have here, and then we are going to put our wafer underneath this mask to capture the image. So, this is a near field imaging. So, unlike projection lithography that requires an additional optics, here we are going to directly put our wafer underneath the mask which contain our designs and then capture the shadow. So, you can also call this as shadow imaging. Let us look at how this system works. So, this is a typical example of a system, right. On your right side you can see here a system at nanoscience department in IISc. So, you have the tower that has all the optics that is required, and then here you see the wafer stage and the mask stage, and then here we see the control, and then here we have the monitor to see all the process parameters. So, the light source and the illuminating optics are located in the tower that we saw. The mask and the wafer is located underneath. So, the basic principle of this proximity printing, as I mentioned, there should be a gap, right. That is the reason why we call this as proximity printing. There should be a non-zero gap between wafer and the mask, and normally this gap is filled with either air or inert gas like nitrogen. This is to keep away any kind of contamination outside this gap. And then, as I mentioned, we are going to capture the near field image. This is a very simple typical setup of a proximity printing. And this is what happens when you zoom into the mask and your photoresist coated wafer. So, this is your wafer, and this is your photoresist, right, and this is your mask. So, we have a uniform illumination that is coming onto the mask, and then there is a gap through which you expect the light to propagate through and reach the photoresist here. But then you can imagine this gap acts as a n number of spherical sources, and then they all will interfere at the photoresist. For people who are aware of this optical principles, so if I have a broad plane wave coming into this small opening here, you can approximate this as a spherical wavefront that is going out. So, if I increase this gap, you can say there are n number of isolated sources, and each source is going to illuminate if the illumination is plane wave, and they will all try to propagate, and then they will try to interfere, right. So, what you see at the end, the profile at the left, this is nothing but your optical intensity that is falling onto this photoresist. As we already saw on upon illumination, this photoresist is going to chemically change and then become soluble or insoluble based on the tone. So, as I mentioned, there is a distance between these two, right, and the image of this mask that you have fall on this photoresist, so that whatever you have designed on your mask will be transferred onto this photoresist, right. So, the intensity profile, as you can see, it is not flat. Normally you would expect a flat profile, right. Ideally speaking, you will expect something like this, right. So, where there is an opening, you will see a large amount of light coming through, and in an opaque region you should not see any light through. But because we are talking about interference here, you will always see some ripple around this, right, and also a gradual decay in optical intensity rather than a step like function. Okay. This is the step function is an ideal scenario, but whatever you get, a ripple sort of thing, and then you go down, this is what you see in practice. Okay. And then we need to know about the resolution of this technique. So, the resolution of the proximity printing depends on the gap and also your wavelength, right. So, W is the resolution, the width depends on square root of your wavelength and your gap. So, this is very much understandable because your wavelength dictates your scattering, right. So, as I already mentioned, based on your wavelength, your light scattering is limited, right. So, if I have an opening based on my illuminating wavelength, my diffraction, right, at the edges are going to reduce. For instance, if this is for a lower wavelength, if I take a larger wavelength, I will choose a different color. So, this is for lambda 1, let us say for lambda 2, I will see a larger diffraction. So, for a larger diffraction, your image is going to look something like this, and if you choose a shorter wavelength, right, a smaller wavelength, then your image will look something like this. So, if you measure the width, right, definitely the wavelength that is lower will always yield a highly refined image, a smaller dimension compared to an illumination with a larger wavelength. So, that is very important to understand while choosing the right wavelength for your structure. For instance, if you want a feature that is about let us say 200 nanometer is what you want, then you should make sure you choose your wavelength that is equal to or less than 200 nanometer. This is very important to avoid any sort of diffraction effects. And that is what you see in the plot below. So, if I increase the spacing, your diffraction actually increases. This is easily understood by looking at this diffracting beam, right. So, if you are looking at this diffracting beam, they always diverge, right. So, the diffracted beam is diverging, and this diverging beam will increase your dimension of structure that you get on the wafer. So, you should be very careful about the gap that we have and also your wavelength that you use. So, for a given wavelength, right, we can trace this 365 nanometer plot. So, as you increase your gap between your mask and your wafer, you are going to increase the line width, right. So for instance, if the spacing is 1 micron, I will get approximately 900 nanometer, right. So if I increase it to about 10 micron, right, now my structure width is going to be about 3 micron, let's say, right. So you should be careful in choosing the right spacing, right, and there is a limit to that, right. There is a limit to the spacing, and the spacing should be greater than your wavelength, and it should be less than your mask width. So this is your width and your wavelength, right. So W square over lambda is your upper limit, and then lambda is your lower limit, right. So one should be cautious about choosing the right gap, right. And what is the effect of this gap? As I mentioned, you are going to have a larger width compared to what you have on the mask. So if mask width is W, then you will have some delta W, right. So this is what you will get, W plus delta W, and this delta W depends on the the penumbra effect that we all knew from high school physics, that any shadow will always cause this penumbra effect, right. And this penumbra effect is going to increase your dimension by this factor, right. And again, this D is nothing but your distance that you have between these two, all right. So we have to be careful about the gap and also your width. So if you increase the gap, you will also increase your penumbra effect, okay. So make sure that you choose the right gap for you to operate, and so that you will get the right critical dimension that you are looking for. And the next type of illuminating mechanism is contact lithography. So here the name itself suggests that it's a contact mode. So there is no gap. So there is no gap. So initially we had non-zero gap. So here gap is 0. Sometimes that is also called hard contact technique, right. So you can either have gap 0 or even push it even further to make a very good contact. So mask and your wafer are in complete contact, right, and this will allow us to have a very good uniform illumination, right. And the other thing is this is also similar to other systems, inexpensive way to fabricate any micro scale device, right. And the alignment is done through the mask itself, right. So so far we haven't discussed how we are going to make multiple layers using this lithography process. All we are understanding now is just an illumination, and whatever pattern you have on the mask gets onto the wafer, right. But if you want to do 2 layers of lithography, right, the first layer you had some device, and in the second layer you say I want to put some electrodes to have electrical contacts. So how do we do that? So that requires alignment, and that alignment is done through this mask positioning and so on. The only problem in this contact process, though it is very simple and you don't need to worry about the gap and so on, this is a contact process, right. So what this will do is it will make your mask dirty, or it will pass on the dirt in the mask onto the wafer, right. This will eventually result in defect in your devices that you are making, right. So one should be careful about the cleanliness of your mask, and also what are all the contamination you have on the wafer. So whenever you do contact lithography, make sure that you wash the mask thoroughly, so that you don't have any contaminants, and also you don't have any particles, because we are going to have hard contact, right. So if this is my wafer, and then if my mask is coming on to my wafer surface here, you will see there is no gap between these two. But if I get to have any contaminants either on silicon or on my mask, when I do this, this particle is going to damage my mask, and also it can get into my photoresist also, right. So, we should make sure that there is no particle between these two surfaces, so that you clean the surface properly. And just for clarity, so this is silicon, you will always have some photoresist, right. Good. So, the technique is pretty straightforward, but you should be careful about the surface contamination and how you are going to handle if there is any contamination and so on. So, the gap between the mask and the wafer, as I mentioned, should be 0, but you can always have some non-uniformity while fabricating on a large wafer. Let's say this is about 100 millimeter wafer, right, and this is mask that you have, and this is a wafer. So, you should have contact across the length and breadth of this wafer, right. So, you should not have any gap, but ideally this is very hard to achieve. The reason for that is you will always have some wafer bowing. So, you could have some non-uniformity in the thickness that you have, and then here I consider mass to be really uniform, but then you will have a contact at the center and you will have some gap at the edge, right. So, in the same way you could also have non-ideal flatness in your mask compared to the wafer. So, this would create some gap, right, unintentionally, right. So, ideally you want 0, but in real world there is nothing like 0, you will have some gap. So, here what we are trying to see is the effect of gap on the optical intensity. So, if the distance between the resist and the mask is 0, right. So, that is if the mask position is at A, right. So, there is no gap at all, then you get this ideal step like response, right. This is what you are looking for. But then if you slowly increase, right, then starts your non-ideal characteristics, right. You see this small diffraction happening and all these fringes that we discussed earlier on in projection proximity printing, right. So, that comes into effect, and then this effect worsens, right. So, it keeps on becoming worse, right. Like I mentioned, you are going to increase your critical dimension because you're going to have this penumbra effect, and then your intensity is also going to go down, right. At some point, let's say in this case F, right, further away from your resist, you still see some reasonable intensity, right, but then it dies down pretty quickly, and then in position G and H, almost you don't have any profile at all, right. So, there are two implications to this, not only the profile, it is also about the intensity of light I have, right. In the last class we saw this resist contrast, right. So, we saw the energy versus thickness of photoresist, right. So, we saw something like this. So, if the energy is too low, so actually I want the energy to be large enough so that I can clear all the photoresist. But now because of this proximity, I am moving away from the contact region here, my intensity is also reducing. So, now I am in this position. So, according to this contrast curve, I cannot expose the photoresist at all. So, you can apply enough dose, but then you will see that there is no reaction from the photoresist. So it will stay there as if you have not illuminated. So this gap not only affects your critical dimension, but also going beyond a certain gap, it will also result in unexposed part or underexposure. Okay. So it is very important to understand what is that level beyond which you will not have any illumination at all. Because the reason for this is in proximity printing, we give some gap, right, and there we know the gap, so that we can actually calibrate our dose, right, or the amount or the intensity of light that we are going to use in this exposure. But in hard contact, always you presume there is a good contact and your dose is going to be dictated by that contact, right. Then when you get this kind of a gap, the structures that are present in those parts, right, will not get any exposure at all, right. So in this part you will not have any exposure, and this part you will have very good exposure, and again in this part you will not have any exposure. So now if you take the wafer, whatever circuits you had at the center of the wafer will be desirable, but then all the devices and the edges beyond the distance that we discussed are going to be out of spec, right, or some of the structures are not even illuminated at all, right. So this process will not yield what you are looking for. So it is very important to understand the flatness of the wafer, the flatness of the mask, so that you can later on understand if there is any failure, where this failure is coming from, and you can address those failures. Okay. So this is about the exposure dose, right. We saw exposure dose is nothing but integration of the intensity over time, right. So over time you integrate how much of light is passing through this desired pattern, right, is what we call dose. So now this is the desired pattern. It has really sharp corners and well defined features, but then when you overexpose, right, so if E naught is your ideal dose, overexposure is E naught plus some delta E, right. There are the different tools calculate this in a different way, but for instance if I am going to illuminate a constant energy for a certain amount of time, right, but now I am going to do T plus delta T, right, same energy, I am exposing it little longer. So that will give me this additional dose. So this is called overexposure. So what happens when you overexpose, right, when you put too much energy compared to what you ideally want, right? So that will result in corner rounding, right. So all these corners become rounded. So whatever features that you are looking for, right, these are all really high resolution corners. So you are unable to reproduce those corners. So we call this as corner rounding. All right. And then what happens if you underexpose, right, that is again an important thing. So E naught minus delta E, right, and that is nothing but I am exposing minus delta T from ideal, right. So now I am underexposing. When I underexpose, again you see corner rounding. This is resolution limited. And another important thing that we should notice, right, is the gap between these two, and also the line width of these features, right. So ideally I had width W, but when I overexpose I am W minus delta W. If I underexpose I am W plus delta W. So when I underexpose, the structure becomes bigger. Okay, so I'm not exposing all the resist that I should be. So the structures are really large. Okay, so this argument will completely flip based on whether you are using positive resist or negative resist. Okay, so one should be aware of the CD loss. We call it as CD loss or CD gain. What is CD? CD is nothing but critical dimension. Okay. So, what is the width? So, in this case W is the critical dimension. So, once you are able to eliminate the structures, and you already have a very nice circuit in layer 1, and now you want to fabricate the second layer. Okay. So, as I mentioned, you might have some capacitive structure here, and now you want to make some contacts, right. I make a larger pad here, right. So, in the first layer you made this, and then in the second layer you want to make this, right. So, more often in your work you will use both multiple layers, right. A single layer process is hardly used, but mostly you will use multi-layer structure, multi-layer patterning to realize your structure. So, it is important to understand how to align layer 1 with layer 2. Okay. So, these are all sitting on top of each other, right. So, how do we do that? So, first the wafer is patterned with the structure that you want, in this case this guy, right, a small rectangle here. So, that is already in the wafer, right. So, now you are bringing the wafer onto the lithography station to do the second layer, right, and the second layer is now on the mask, right. So, this layer is in wafer and this layer is in mask. So, now you should find a strategy to align these two together, and that is where we use some alignment markers, right. So, feature on the wafer should, for instance, if you are going to put a cross there, right, and in the on the mask you are going to put a cross that is covering this whatever alignment cross that you had, right. So, now if you want these structures to be aligned, right, you will put cross and cross, right. That means this is from the mask, this is from the wafer, and this is from the mask, right. So, if you can align on this one on one, right, then your structure also aligns. You see here. So, this was the structure on the mask, right, and this was on the wafer. So, I am just aligning this feature onto this feature, right. So, it is impossible to do this structure by structure, right. You might have hundreds of devices on the mask. It is impossible to align each structure. So, it is better to put alignment markers and then only align the alignment markers that should take care of device alignment as well, because this is all relative positioned, right. So, once you have this one, and then you can align this, and then you put the contact and then start illuminating, right, and you should be able to get the aligned illumination that you are looking for. So, in order to understand how to put these alignment markers, let us look at the alignment marker placement, right. So, if I take a circuit, right, and then I have some circuitry, right, let us say something like this. In the middle, I always put the alignment markers at the corner, right. If you are want to be very careful about this, you can also put more number of alignment markers, right. So, these alignment markers are very important, not just to put these two structures on top of each other. It will also allow you to avoid any kind of rotation, right. So, if you could have some rotational misalignment, right, and just the four corners may not be sufficient to take care of these alignment problems. So, that is why having additional markers are desirable to avoid these sort of misalignment, right. So there are a number of alignment strategies, but these are all very simple alignment strategy that one can use if you want to align these features. And to summarize contact lithography and proximity printing, so the major advantage of this system is these systems are very simple to use, right. The cost of ownership, the amount of money that one need to spend in maintaining these structures or system is very low, okay, and that's why we use it quite a lot in R&D and research work. But only limitation of this is the critical dimension or the resolution that you can achieve, right, because this is a contact lithography and we use a mercury vapor lamp, for instance, then you are limited by the wavelength of your mercury vapor lamp that you can get, right. So at the max you can go to deep UV, right, because mercury vapor lamp emits deep UV. Right. And the other problem associated with this system is damage it might cause, right, because you are either in contact or in proximity. And that is the reason most researchers they tend to go for a small gap between the mask and your wafer, so that you don't have any hard contact and then scratch or whatever defects one can generate. So though this is limiting for a lot of high resolution application, but it is a workhorse for a lot of MEMS technology and also for devices and circuits that requires larger features. Very simple to use, straightforward, no complex optics, very easy to maintain the tool and so on. So a lot of the R&D establishments use this, right. And other thing that I should also mention is the lifetime of the mask, because you are in contact or proximity. Even when you call it proximity, you might touch some time. So this contact will create some damage to the mask, right. So that will reduce the mask time, though you can use the mask a number of times. So the lifetime reduces the more you use because of the defects that you create. So I hope most of you got a good grip of what this contact and proximity printing is all about. And in the next lecture we will see how projection lithography works.